Hello everyone, this is Engineer Selassie from Hello Academy in Brain Boosters. Today I came up with another chapter. So this chapter will include chapter 11, 12 is just a dialogue between the student and the professor. I encourage you to go ahead and read it. It will give you a good idea. And in this chapter we are going to discuss about the abstraction. What is address space? So let's get into it. So what is a memory virtualization? What is a memory virtualization? Operating system virtualizes its physical memory. So operating system provides an illusion, memory space per each process. When the process runs, it thinks it has its own memory. So it seems to be seen like each process uses a whole memory. This is the abstraction which the operating system does. Benefit of memory virtualization, ease of use in programming, memory efficiency in terms of time and space, it guarantee of isolation for process as well as operating system, protection from errant access of other process, because when one process runs, it will not affect the other process, or any security issue will not be there. So operating system, in the earliest system, batching system, what we have is operating system is just a library. A library means it doesn't have any power over the running process. Just it will give loading, unloading, something like that. So it's just a library. Load only one process in the memory first. We have the first part will be the operating system, the code, the data, and the current program will be under the operating system. This is the physical memory. So load only one process in the memory, execute until completion. That was the batching system. Poor utilization and efficiency, because no other process will be allowed until the running process is completed, or there is no time sharing, or this kind of multi-programming system is not at this level, will not be allowed. Poor utilization and efficiency. CPU is idle when process is doing I/O, because when it goes for input-output operation, no other process will be in the CPU. Other process can fit in memory. So that was the idea of operating system in the batching system. Multi-programming and the time sharing. This is the second. So in the multi-programming and time sharing, what it does is load multiple processes in the memory. As you can see, we have process A, process B, process C. Code and data will be loaded in the memory and execute one for a short while, and the switch process between them in the memory, because it is time sharing. It has a time quantum. So when one process go for input-output I/O operation, then another process can run in the CPU. So result, increase CPU utilization and memory efficiency, and system becomes more interactive compared to doing just batch processing. In the first, what we see here in the batching, only one process was here and there is no interaction. But in a multi-programming system, interaction is there. Cause an important protection issue, because most programs are running, so one program should not be allowed to interfere or read or delete the other. So this multi-programming and time sharing concept raise a protection issue. What if a user process access another user process or kernel? So this was the idea in the multi-processing and time sharing. Abstraction, address space. What is address space? So OS creates an abstraction of physical memory, which is called address space. So when a process runs, it thinks that it has its own memory. So the address space contains all about a running process. The running process, as you can see, we have the program code here, we have the heap, and we have the stack. This is free, 16 kilobyte. The address space of a process is 16 kilobyte. So the address space contains all about a running process. A running program owns own view of a memory, its memory state. So the running process thinks it has its own memory. That is address space of a memory, virtual memory. Important, it is not the actual location in the physical memory. So it is not an actual location in the physical memory, it is just a virtual memory. That is consists of the program code, heap, stack, and etc. As you can see, we have the program code with the heap and the stack, everything is in the address space. So every process has its own address space, which it thinks it has its own full memory, but in reality it is not. So it is an abstraction which is created by the operating system. So the address space, as you can see, the code here, the program code where instruction live. The heap is for dynamically allocated memories. We use malloc in C language, new in object-oriented language, and the stack store return addresses during function calls or return values, contains local variables or actual parameters. So stack and heap are different. Heap is for dynamic allocation and the stack is just static. So we have a program code. So the virtual address, as you can see, virtual address, just the operating system is responsible to convert the virtual memory to the physical memory. So as you can see, every address in the running program is virtual. That means operating system translates the virtual address to the physical address. Then a simple program that prints out virtual address. For example, we have this program. OS translate the virtual address to physical address. As you can see, this is also from the textbook. You can see it. We have int main, we have int argc, character argv. So printf location of the code, and printf again location of heap. Okay, location of heap, and we have malloc1. So int x is equal to 3 and print location of stack again in the location of stack. So let's see this. I think it's better if we see it in the code. So what we are going to do, let me open this code and let's run and let's see the location of the code, the location of the heap and the location of the stack. Let's see. So what we are going to do, we have Linux. So so this is a code. Again, the code you can download it or you can write it. So if you see, so we have VA. So this is a code, view va.c. So this is a simple code. As you can see, location of code, heap, and stack. So these three codes we will see. So what we are going to do, we're gonna compile it. Okay, we're gonna use this formula. Yeah, GCC, you know it. Yeah, GCC va.elf va.c. So it's running now. Now let's invoke it, va.elf. So as you can see, the location of the code, the location of the heap, and the location of the stack, this is in hexadecimal places. You can see this is virtual memory. So we have to convert this virtual memory into the physical memory. We will see it later how we use the other concepts. Okay. So with the code, we can see where the location of the code is, where the location of the heap and the stack. And play around, you can see a lot of other things. And the virtual address, as you can see, the output in the 64-byte Linux machine, the code, the location of the code, the location of the heap, and the location of the stack was already, we got it, we have seen it now. So we have the address space here, we have the code, data, heap, and the stack also we have here. So all these values were identified. Okay. So in general, goals for a virtual memory system. The goal of a virtual memory system is, the first is transparency. That means implementation should be invisible to a process, and the process behaves as if it has its own private physical memory. But in reality, it doesn't, because we have only one physical memory. Second, efficiency. In terms of time, not make process run slowly, and space, not much overheating the memory use. This is the goal of a virtual memory. And we'll need to rely on hardware support like TLBs, etc. So TLB means a translation look-aside buffer, is a type of memory cache that stores recent translation of virtual memory to physical address to enable faster retrieval. This high-speed cache is set up to keep track of recently used page table entries. Protection and isolation prevent a user process from accessing other user process of the kernel. That's also the idea. So in the nutshell, it's very short video, and as we have seen, the goal of what is virtual address space and how to get it in the Linux and the Linux program, everything we have seen. So we will come in the next chapter, which will be chapter 14. Till then, thank you so much. I hope it was helpful, and bye bye. This is Engineer Selassie from Helio Academy and Play Boosters.